Thanks for the invitation and the introduction. So today I will talk about positive scalar curvature manifolds in 3D with bounded geometry and some classification results. So first, let's start from closed 3D manifolds with PAC metric. So throughout this talk, I'm going to abbreviate positive scalar curvature as PAC. So after Paraman resolved the Poincaré conjecture, we have a full classification of the closed 3D manifolds with PC. So any closed, let's say oriented 3D PC, it must be diffeomorphic to a connected sum of the following manifolds. So first, it could be the first type of factor could be a spherical space form, or it could be S2 cross S1. So there are obvious PAC metrics on these connected sum factors. Okay, so for open manifolds, if we have infinitely many these two factors and we take the connected sum, we can also form a PAC open manifolds. And for example, the simplest PAC open 3D manifolds is R3. So we can view this R3 as a connecting sum of infinitely many S3 with one end. And also we can have this another PAC manifold, the cylinder R cross S2 as a PAC manifold, which is also a connected sum of these guys. And then, based on this observation or some other intuition, Yale made this following conjecture. So, can one classify all the open 3D manifolds with PAC? And a subconjecture of this open question is the following. So if we add one more condition, assume the manifold is contractible, and then the subconjecture says that it must be diffeomorphic to R3. So 3D open PC and contractible must be diffeomorphic to R3. And so, so far, this subconjecture still remains open, but there's some
Sorry,
partial.
you
Yeah.
assume your PSC metric is complete, right? Or
Yeah. So I always, when I say open, I mean, um, this is means non-compact. Yeah, thanks for the question. So non-compact but complete. Yeah. Mhm. Yeah, so this subconjecture has a partial answer by Jing Wang for genus 1 manifolds. So genus 1 uh, contractile manifolds means that this manifold admits a exhaustion by a sequence of torus. So if it is contractible and 3D genus 1 manifold, for example, the white-hat manifold could be such an example, then it does not admit a PC metric. Okay, at least this partially confirms this conjecture, subconjecture. So it cannot be white-hat manifold and any other genus 1 contractible manifold. And if we have a stronger curvature condition, so not only the scalar curvature is bounded below by zero, but it has a uniform lower bound, uniform positive lower bound, and then there are also some partial answer to this subconjecture. So the result of Bissell, Benson, and method states that if one has this open 3D open manifold, but the scalar curvature is bounded uniformly by 1, and there's a bounded geometry, which is a condition I'm going to say in a second. And then they use the Ritchie-Floyd surgery and show that the manifold must be a connected sum of the spherical factors or S2 cross S1. And so here the bounded geometry condition, so BG, uh, is also the condition we're going to use for our result. So it means bounded geometry, and so the curvature operator is bounded everywhere by C, and the injectivity radius is greater than equal to C minus. Okay, so the advantage of this assumption is that we're allowed to, we'll see that we can take limits of manifolds with these conditions, and it will um, converge to some smooth manifold. Okay, so with this additional assumption, they confirm the conjecture and get even better structure of the underlying manifold. And later, Gen 1 was able to remove this uh, assumption of boundary geometry by using a minimal surface method. So now it is known that any open 3D manifold with r greater than equal to 1, it is a connected sum of these factors. Okay, so in the following, we state our first result. So we confirmed this subconjecture under this uh, weaker condition, so PC condition, and but we so under also this boundary geometry condition, we show that the manifold must be R3. So, so this is joint work with Otis Chodosh and Kai Xu. So we show that any 3D open manifold. So we even allow that scalar curvature to be bounded below, being bigger than equal to 0. And it has bounded geometry, and it is contractible. And then it is diffeomorphic to R3. Okay, so that's our first theorem. And on the other hand, we see that without this contractible condition, there are still another non-PAC open manifold, which is the R2 cross S1. So it is diffeomorphic to the solid torus, but as you asked, we require that this has to have complete non-compact metric. So one such metric with PC could be constructed by first taking a metric on R2 with positive sectional curvature, such as this cigar-like manifold on R2, and then cross it with H3, and then it would have a PC. So this manifold, it does have PC metric, scalar curvature is positive, but not but note that this not does not have this scalar curvature bigger than equal to 1 because all such manifold has been classified and this is not one of them. Okay, So if we remove this contractibility condition, we have to at least include this manifold. And the natural question, since this is the genus 1 handle body, I will have the following natural question, which is, do we have PC matrix on other handle bodies? So does any handle body admit a PC metric? So here I'm also assuming that it's a complete metric. The completeness is necessary because otherwise you can just embed this handle body into R3 and it will have a PC metric, but it is not complete. Okay, so for this question, let's start from low genus handle bodies and see what we have. So genus 0 handle body is just R3, the diffeomorphic to the solid disk. And yes, it does have a PC metric, and just as we see above, the genus 1 handle body, which is a solid torus, it also has a complete PC metric. So answer is still yes. And now the question is, what about those handle bodies with genus greater than equal to 2? And so this is unknown. This is unknown now, and our second theorem showed that they could not admit a PC metric if the metric is has bounded geometry. So theorem B. So still collaborated with Otis Chodosh and Xu Kai. So we show that if we have a complete Riemannian metric M3G, which is diffeomorphic to a handle body, and it admits R bigger than equal to 0 and satisfies bounded geometry condition, and then the genus cannot be bigger than equal to 2. So only these two cases can happen under this bounded geometry condition. Okay, so that's our main theorem, and our tool to prove these two theorems is uniform, which is using the inverse mean curvature flow. So in following, I abbreviate as IMCF. So in the next um, few minutes, I'm going to give a short introduction to the inverse mean curvature flow and summarize some results we're going to use to prove these two theorems. Okay, so first let's start with the definition of the inverse mean curvature flow. And first we define it in the smooth sense. So we say a function gives a smoothing curvature flow if this function u is a smooth function of an open domain omega. The omega is an open domain in a Riemannian manifold. If gradient of u is never zero and the function satisfies the equation divergence of gradient u divided by uh, the norm of gradient u is the norm of gradient u. Okay, so that's the equation of the function, but it was so if we look at its level set, and then the name of inverse mean curvature flow will make more sense. So the level set ET is defined as the point where UT is less than T. So ET is the sublevel set of U, and the boundary we define it, we call it a partial ET, So t is the dependent time. And then we can show that this family of surfaces solves this equation. So the evolution is given by 1 over h in the normal direction. So this is because so this divergence of this vector. So this vector is the normal vector of the level set, and the divergence of normal vector is the mean curvature. And so this is the mean curvature, and this is 1 over the normal speed of the level set. Okay, and so that is how we get this evolution equation. And just a quick consequence of this evolution is that we can compute the evolution of the area form and thus integrated on the entire surface. We get that the area of partial ET satisfies this equation. And integrate this in time, we have that partial ET is e to the t minus s partial es. So this means the area of the level set partial e at time s, and so for any t and s. So this is the definition of inverse mean curvature flow with in the smooth setting. And next, we talk about the weak inverse mean curvature flow, which is introduced by Huisken and Immonen. So what is a weak inverse mean curvature flow? So now we weaken the regularity requirement of U. So we only need that U is a locally Lipschitz function on omega. And we say that U solves the weak inverse mean curvature flow equation if its level set is a local minimizer of a energy functional. If any level set E, so we omit the dependent of time here. So for any level set E U, it is the minimizer of the following energy functional. So the energy functional is defined in this way. So first we have a compact subset K. So K is the dependence on K is here, and a function U, and competitor F. So F is going to be defined later. So this energy is defined, energy function is defined to be partial F intersect K. So the area of partial F inside K minus integral of gradient U F intersect K. And so this is a function energy functional. And what do I mean by minimizer? Sorry, a local minimizer. So a local minimizer of this functional just means the following. So that is for any compact subset K and any subset F, the competitor F with so the difference of F and E, which is the union of F minus E and E minus F, is contained in K. For any such F and K, we have that the energy functional at of U at E is always smaller than equal to the energy functional at F. Okay, so let me draw a picture of what this E and F look like and how this is should be understand. So suppose this is in the entire manifold is just omega, and here is the level set E. So this inside part is E, and uh, we have a compact subset. So this is our compact subset K, and what is the competitor competitor F? So F could be so it has the same of so outside of K it is the same with E, but it could be like this. So the inside region, this region, so the inside is F. And so this is a competitor of E. And uh, so the energy functional is always locally minimized by the level set. And in particular, what we're going to use often is a special case of this minimizing property. That is using this minimizing of energy, we can see that the level set always locally outward minimizes the area. So in particular, this implies E is locally outward minimizing in the following sense. So for any compact subset K, and if F is bigger set, if E is containing F with F minus E is containing K, and we have the following comparison of the areas. So partial F intersect K minus partial E intersect F is greater than equal to F minus E gradient U. And so this is bigger than equal to 0 because this gradient of U norm is non-negative. So this can be read off by just using this definition and this minimizing property. So in this case, we choose F to be a subset containing E. And so that's why we see this locally outward minimizing, because for any such F, the partial E always has a smaller length or smaller area. Okay, so uh, uh, for let me give an example of this locally area minimizing property. And say we have an open manifold like this. Okay, and so let me I see. So we want to start an inverse mean curvature flow from a very small neighborhood at the rotational center. So suppose this metric is just a rotational symmetric. And then we start from a very small neighborhood from at the center, and then the uh, flow flows outside, and so until so at some time capital T, the area of ET is the same as the area at these regions. And then the flow will jump not to the first place that is has the same area, but will jump to the last such region. So we'll jump to here. Okay, so then by using this inequality, we could see that because this area is equal to this area, so we could take this as E and take the entire thing this entire thing up to bounded by this circle as if. So take this as partial if and inside the region as if. And using this inequality, we could see this has to be identically zero. So this is zero means that this middle region have a vanishing gradient everywhere. So for the weak mean curvature flow, the gradient can actually be zero in such a large region, and this behavior, this phenomenon, we call it a jump of the inverse mean curvature flow. So on this shadowed region, we have U is a constant equal to T. Okay. And so in this case, partial F is equal to partial ET. So this is we say that the inverse mean curvature flow jumps at time t. Okay, so well, to summarize the property of weak inverse mean curvature flow, it is determined uniquely by two properties. So first, it is the 1 over h flow when it is smooth, when the gradient is non-vanishing. And it jumps to the outermost minimizing hull if it fails to be smooth. So outermost minimizing hull. So in this picture, it jumps to this circle because this circle is the outermost minimizing hull. And another example, a bad example where the inverse mean curvature flow could not exist for even a short positive time. So this could happen on such a manifold with a very thin and vanishing cusp. So the length of this, the diameter of this cusp goes to zero at infinity. And no matter how small we choose the initial level set E0, it is not going to be any other solution except being zero for all the outside regions because this circle is always for this one initial condition, we can always find a much smaller circle at infinity, which has a smaller area. So there is no non-trivial solution on this manifold except the constant one. Okay, so here we're going to see more properties of inverse mean curvature flow in the proof, but these are just some basic facts we summarized. So in the following, we state the theorem that will imply theorem A and B at the same time. Also, we showed, also still in the same work. So if M3 complete 3D manifold is contractible or handle body and has PC boundary geometry, and then we can find an exhaustion by S2 or T2. So then there exists an exhaustion sequence by open domains omega 1 containing omega 2 and their union is the entire manifold with the boundary of them is either S2 or T2. Okay, so So your remark of this theorem. So using this theorem and together with some topology argument, we are able to show that theorem A and theorem B is true. Okay, so this is a condition in theorem A and this is a condition in theorem B. And after finding such exhaustion sequence, we can show that the topology must be either R3 or a low genus handle body. Okay, so now in the following time, I'm going to discuss a sketch of this theorem and show you how to find the exhaustion sequence by this is 2 or T2. So proof. So to begin with a proof using inverse mean curvature flow, we have to make sure that we can find a non-trivial inverse mean curvature flow on this manifold. And this is exactly where this boundary geometry comes into play. So by a previous result by Xu Kai, he showed that with this boundary geometry condition, although he showed this theorem in a more general setting, but what we need is the boundary geometry setting. So if we have this condition, and then we can start from a very small geodesic ball, so that the inverse mean curvature flow could exist for at least a short amount of positive times. So this is non-trivial. So starting with E0, so E0 is the initial level set, which is the geodesic ball with very small r naught. Okay, so the existence of the inverse mean curvature flow is guaranteed by the boundary geometry condition. So that boundary geometry just also rules out this cusp-like structure. Okay, and we can show that there are three types of different behaviors of the inverse mean curvature flow. So we can show that U is must be one of the following. So first, it is a proper inverse mean curvature flow in the sense that all the level set is a pre-compact subset. So that's the simplest case. So every level set is pre-compact. There may still be jumps every now and then, but every level set stays pre-compact. And the second case is called sweeping. So the sweeping case is that so the flow exists a positive time, capital T, so that before this time, every level set is still pre-compact, but after this time, at exactly this time, the level set becomes the entire manifold. And so so that's what we call it sweeping. So the level set at time capital T rushed into swept the entire manifold instantly. Instantly. And the last case is called escaping. So the escaping is slightly different than sweeping. So there is a still positive time and up to this time, it is still compact, but then outside of this, the last compact level set, it is a constant. Okay, so I'm going to draw some pictures for each of these different cases. Okay, so now I'm just gonna assume these three types of behavior and continue with the proof in different cases. So this is a general discussion without using the positive scalar curvature assumption. But in the following, we're gonna use it in a non-trivial way. So first, let's discuss the proper proper case. So when U is proper, that's the
Might I
simplest.
ask a question?
Yeah, sure, sure.
Hi, sorry. Um, this is the point. Uh, is the Kaishu result the only place where you're going to use the bounded geometry, or do you use it again to get the three
Oh,
cases.
yes. You will see that we use it again in taking a subsequential limit of the level set. So basically, you will see that the boundary geometry guarantees the diameter bound and the regularity of the level set. Yes, that's
Oh,
also
thank you.
yeah.
Thank you.
Sure. Thanks for the question. Yeah. So in the simplest case of the proper inverse mean curvature flow, the nice thing is that we have the Geroge inequality. So it is discovered by Huisken and Imanen. It says that if M3G is a PC, admits a PC complete manifold metric, and the U is a proper inverse mean curvature flow, and then we have the monotonicity of the integral of the mean curvature square, and then we have the d by dt. Okay, and so using this monotonicity, we could see that we can find a sequence of Ti going to infinity such that this term is non-negative. Because if there does not exist such a low such a sequence with the Euler characteristic being non-negative, and then this is gonna be a negative term, and running the flow for a while is going to make this non-negative number to be a negative number, and that would be a contradiction. So in order to make sure that this term is always non-negative, this Euler characteristic of the level set has to at least be non-negative for say at some sequence. And then that implies immediately that this level set is S2 or T2. So in this simplest case, we used the monotonicity formula to find out that the exhaustion is exactly given by the level set of a inverse mean curvature flow. Okay, so that's nice in this case. And the second case is more complicated. It's called the sweeping. So when would a inverse mean curvature flow have this behavior? So for example, if we have such a sorry, such a cigar-like manifold. Imagine that this is rotation symmetric, or just it, and it has bounded width at infinity. And then we can have this inverse mean curvature flow starting from any geodesic ball, E0, and this could be E t minus epsilon. And when epsilon goes to 0, so this is E t minus epsilon over 2. And let's see, epsilon I. Epsilon I plus 1. And so as the time little t goes up to capital T, the level set is going to move to the infinity of this manifold. And so we see this t to be the sweeping time. And in this case, we're going to also use this inverse mean curvature flow to give us the desired exhaustion, but with more argument. Okay, so choose a sequence of times ti goes up to t, and take a point pi on the level set partial eti, and then the mgpi. The pointed manifold, so pointed at pi, with the bounded geometry condition, we can show that it smoothly converges to a manifold, which we call M infinity, G infinity, P infinity, and also that it inherits the non-negative scalar curvature condition because that's a smooth limit. And along with the limiting with of the based point manifold, so say this is our point pi. This is pi plus 1. We can show that this level set will become more and more area minimizing. So it is almost, in some sense, area minimizing. Okay, so why this is true? So we can look at this level set, and for a subset which is outside of this level set, which we fix this I, the area is gonna be smaller. The area is gonna be bigger than or equal to the area of this level set because the inverse mean curvature flow is outward minimizing. And also, even for the region which is not outside of the level set, such as this one, it has some point inside of this level set. But as long as we know that this level set is outside of the last level set, so this is a last level set, and this green subset is outside of it. Then we can use the locally outward minimizing property of this level set, of the last level set, and say that this guy has an area which is bigger than equal to this level set. But we know that this level set has almost the same area with this level set. So this level set is has a almost a smaller area than this competitor. So in this sense, it is almost area minimizing as long as we choose the distance between two level sets to be sufficiently large, arbitrarily large. And we can also show at using some other property of the inverse mean curvature flow that it is also connected and has bounded diameter. So bounded diameter is a consequence of the bounded geometry because we know that bound geometry gives a lower bound of the area, but at the same time, if the time is bounded, we have a upper bound of the global area. So this implies bound diameter. And also we have a local uniform C1 alpha regularity. So the level set is C1 beta smooth. And so with all this information, we can also take a subsequential limit of the level set based at Ti. So which would be this level set going to infinity. And in C1 alpha sense, for any alpha smaller than beta, we can now show that it converges to a C1 alpha surface, sigma infinity, based at the same base point, P infinity. So this is a surface in the limiting manifold that we get before. I know that this manifold has a PC and also this is area minimizing. So the almost area minimizing becomes the exact area minimizing after we take in the limit because the region where it minimizes area becomes larger and larger and eventually it covers the entire manifold. And then luckily by the result of Shungyao, we know that this minimizing subset sigma infinity must be S2 or T2. Okay, and thus implies that for any large I, sigma I is also diffeomorphic to S2 or T2. sorry, no, sigma I is just the level set of Ti. So in this case, we also find a sequence of exhaustions by the inverse mean curvature flow level sets. So that's the sweeping case. And the last case, which is the most uh, difficult one, is the escaping case. So in what manifold would we have such a escaping inverse mean curvature flow? So we could have such a another rotation symmetric example. Okay, so we can start from a very small level set, and that is going to flow smoothly for a while. The level set stays compact, pre-compact, and until some time, which is this level set, capital T, so ET, and at this time, the area of the level set becomes the same as the limiting width at infinity. And then it is going to jump immediately to infinity. So this length is the same asymptotic width at infinity. And so therefore it jumps at this time. So U is equal to capital T in the entire outside region. Okay, so in this case, we could not expect to get an exhaustion by the level set of the inverse mean curvature flow because the level set just becomes non-proper starting from this time. So it does not give us an exhaustion directly. So what we do is the following. So first, we're going to find an exhaustion, although we don't know what's the topology of this the exhaustion sequence, but we could make sure that there exists an exhaustion partial omega k. Oh, sorry, exhaustion by open domains omega k, so that the area of the boundary converging to the area of the level set at the jumping time. So in this picture, this is also the width of the uh, circle at infinity. And so this is uh, also used by running another inverse mean curvature flow with a barrier. So with this so-called um, so this uses uh, Cauchy's maximal inverse mean curvature flow. So that is the inverse mean curvature flow with boundary. And so the boundary guarantees that the inverse mean curvature flow cannot jump outside of this boundary. And so therefore it stays compact. Okay, so I'm going to skip this part. So we can find such an exhaustion sequence, which in this picture is just these circles. So it's just these circles. And next, for any such exhaustion, so let's see, this is a partial omega k. And we can do the following perturbation on the metric. So we're going to find another nearby metric. So I'm going to define a new metric G tilde K, so that G tilde K is the same with G within omega K. So on this region, it is the same with G. And that's the first thing. And the second thing, we want it to be slightly fatter than G away from omega K. So G, K, G to the K is 1 plus epsilon times G away from partial omega K. And so in this picture, what we mean is that we fatten it a little bit at infinity. So this is the new metric G tilde K. Okay, so now with this new metric, so it is slightly bigger than the original metric G, and this allows us to run a new inverse mean curvature flow with the same initial condition, but now it would exist for a slightly longer time before it jumps. Okay, so now consider the inverse mean curvature flow U to the K on M G to the K. It still has the same initial condition. And then we have for some T, for some T slightly larger than the jumping time of the original inverse mean curvature flow, we can show that first, the level set of the new inverse mean curvature flow won't jump to this region. Okay, because this little t is not much larger than the capital T, so we still have an area bound. And so if it jumps to this region, then the area is going to be too large, and that's impossible. So we have that this won't jump to the region where the metric is strictly bigger. And so this, on the other hand, we also guarantee that because we also guarantee that the level set will jump outside of this region of omega k. So partial ET u tilde k won't stay within omega k. Okay, so this is because also we can prove by contradiction if it stays inside of omega k. But we know that little t is bigger than capital T, so the area is going to be bigger. And by the exhaustion sequence we choose, the area of partial omega k is almost equal to the area at the jumping time. And this choice of little t would give us that we have a level set with area which is bigger than the area of this guy. So it cannot lie inside of this boundary. Otherwise, it contradicts the outward locally minimizing property. Okay, and so now with these two properties, combining them together, we find a level set partial t u to the k, which is not, which is still pre-compact, and it jumps to a region which is outside a compact which is outside this omega k. And since omega k is an exhaustion sequence, we could repeat what we done in the second case, in the sweeping case, and let k goes to positive infinity, and this level set. So note that this k may depend, this t may depend on also k. So this level set also forms an exhaustion, a new exhaustion. And it has more properties than the original exhaustion by omega k, in the sense that now it has bounded diameter and the bounded regularity, and also almost error minimizing. And so just by taking the same limit as in the second case, we can show that this level set converges to sigma, which is diffeomorphic to ACE2 or T2. So thus we finish this proof of the Mann theorem, and it implies theorem A and B. Okay, so I'm to stop here. Thank you very much for listening.